Welcome, everyone, to the next in our wonderful series of inaugural lectures. They're always a highlight for me to attend these. For those of you who don't know me, I'm Rachel Barron. I'm the Executive Dean of the Faculty of Natural, Mathematical and Engineering Sciences. And tonight we've got a real treat. I always like to start by thinking, what have our speakers got in common? So we have two speakers tonight, Simon Banks and Giovanna Tinetti, who are both part of the NMES faculty leadership, Vice Dean Education, Vice Dean Research, and both joining us after more than 15 years at UCL. So Simon joined in January 24 and Giovanna in June this year. What I probably care about more, though, is the fact that they're both completely committed to working collegially across the faculty, working with departments, getting into the departments, working with those key people like the deputy heads for research and education, working with academics, working with professional service colleagues, and working as part of the faculty leadership team closely with the heads. So it's an absolute delight to be able to introduce our speakers tonight, because I've had a chance to get to know them as colleagues and people who are a real pleasure to work with. So first of all, we're going to be having Simon lecture to us, Simon Banks. Simon actually began as a natural science student at Cambridge, very, very briefly, before he saw the light to come to London, transferring to UCL to take his chemistry MSci degree, his integrated masters, and then PhD. He took a few years away to Oxford doing postdoc, before then returning to UCL in 2009 as in the chemistry department there. And he rose the ranks in chemistry, undertaking responsibilities for education leadership, and then moved over to engineering, where he was the Director of Education and Faculty Tutor there in the Faculty of Engineering at UCL. And as I said, very fortunate for us, joined us at King's nearly 2 years ago now as our Vice Dean Education. So in Simon's research, he looks at the statistical mechanics of model magnets and the quantum dynamics of reactive collisions, and is certainly no stranger to mathematics in doing that, as I had the delight to be a substitute lecturer for his course for first-year chemists in maths last week, which is incredibly well received, which is quite an achievement, teaching maths to chemists and being a popular lecturer, so well done for that. So at KCL, in his leadership role, he's been instrumental in launching the Natural Sciences programme as part of the King's Interdisciplinary Science Major Investment Programme. He's also playing a really crucial role in our work on integrating engineering across the college. He's been a total right-hand man and key college person for recruitment, admissions and marketing, so that we are able to attract and recruit fantastic students to our great programmes. And, you know, if that's not enough, he has done transformational work on our student experience. So we had a 10% increase in the engineering department, which was in no small part due to Simon's efforts and collegial working with the department there. So I think it's time to be over to you, Simon, to educate and entertain us for half an hour. I think it's almost time.
Oh, half an hour. Okay, right, here we go. Thank you very much, Rachel, for that lovely introduction. It's going to be a little bit of repetition now, because the first part of my talk is telling you all the things I've done before I arrived at King's. It's a real pleasure to be here. It's a bit of an indulgence, an inaugural lecture. It gives you a chance to think about your career to date and think about the people who've helped you along the way. And so I'm going to talk for a few minutes first about those people. Those of you who are fans of Douglas Adams might recognise the interconnectedness of all things. That's a reference to Dirk Gently, not Hitchhiker's Guide, but his other famous series. And that quote, I think, sums up in many ways my approach to my career to date. Don't always have a plan for where I'm going, but I seem to have ended up where I'm meant to be, and that feels very comfortable. And I certainly feel that being here at King's as Vice Dean in NMES is a really good fit, and I'm enjoying it greatly. So, if I've ended up in a certain place, how did I end up there? As I say, the first part of the talk is going to be looking at this, but probably the best bit of this is really, you make decisions along the way, you have a bit of luck, but it's really about the generosity of other people, and that has been what's characterised my personal journey. So where did it all begin? It began down on the south coast of England, and not in 1995, because that's when I was born, that's when I started my A-levels, so you can do the maths on that one, I'll leave that to you. Probably greatest support through my early years and a lot of my later life as well, my parents, not least because before I arrived at Chester College to do my A-levels, and more of that in a minute, my dad here was the person who taught me maths, and he taught me maths at school. He was a maths teacher for his whole career, and my mum was a teacher as well, so education was really right there up front and centre in my upbringing. But probably he taught me more maths whilst doing the washing up after Sunday lunch, whilst he washed and I dried, than we ever did actually in the classroom. I was also lucky to have a fantastic chemistry teacher at school, Charlie Cleary, who gave me an A-level chemistry book when I was doing my GCSEs, and that really set me along a particular path. And probably the best bit of advice my mum ever gave me was, don't do all that stuff you're doing to become a medical doctor, because you might be good at the technical side, but the rest of it probably isn't going to work. I went to Chester College, as I say. That was the place I did my A-levels. Very large further education college, about 5,000 students, most of whom were doing vocational courses, and A-levels was a small block. We had a lot of fun. I enjoyed the study, I enjoyed the basketball, and I did my science things, and I didn't really know where I was going. But Dr. Waller taught me chemistry, and she was pure effervescence in terms of her enthusiasm. She was a marvellous teacher, and it's for that reason that I went into chemistry for my degree, which I did at UCL. UCL back in those days, this was 1997 to 2001, and really it felt like a very young and dynamic place. A lot of the staff were quite young, and there was a great atmosphere. I can't possibly list everybody, but what you'll notice here as I go through these points is a lot of back and forth over the years. People come back round in their influence in my life. This is Mike Ewing, sadly passed away in 2016. He taught me statistical mechanics. He taught me thermodynamics, and probably more than that, he taught me programming. I'm not sure he actually taught me programming. He gave me a floppy disk with a Fortran 77 compiler and a batch file and a booklet and said, all that stuff that we're doing over there on Excel, you can do it in much better ways. Have a look at this. And that set me on a path which probably set up most of the rest of my career. And then this is David Clary, with whom I did my master's year, now Professor Sir David Clary. He was at UCL at the time and gave me lots of good advice. Not least was the fact, and this is somebody who, I don't know, he's got an H index of somewhere approaching 100 and has published hundreds and hundreds of papers. But he told me once, don't forget when you're marking a student's work how important it was to them when they were doing it. And I thought that's an interesting balance for somebody who's got that particular research profile. Okay, so that was my degree, and at the end of my degree I did fairly well, and well enough that they gave me what was called a graduate research scholarship. So I had my own money. That gave me flexibility, because then I could go to supervisors and ask them if they'd have me, rather than having to go to people who had the funds. But there was only one person in the department, certainly, that I really wanted to work with, and I'm really pleased that he's here tonight. It's Professor Steve Bramwell, who's now co-director of the London Centre for Nanotechnology. And Steve was doing work that was both interesting and mysterious, because it really strayed at the edges of what an undergraduate chemist really understands. But the thing that really drew me to what Steve was doing was the fact he always had a smile on his face, and he always seemed to be enjoying his work. And I thought, I want that in my life. These are just some of the things you do in an inaugural. These were the fantastic people that I worked with in the office at the time. But I think it's interesting, the gender balance in that group, bearing in mind that that was the group of hardcore theoretical and computational chemists in UCL in the early 2000s. This was 2001. So I think that's and it was a fantastic group of people to work with, as was this person here who came back as an influence later on and set me up with some contacts. It's a person called Andrea Taroni, who subsequently went on to become chief editor of Nature Physics, and is now a major player in the Nature group. After my PhD, which was on statistical mechanics, was on critical systems, so I was really looking at the behavior of fluctuations in highly correlated systems at critical points. I did a volte-face and went back to the kind of work I was doing with David before, and that was on quantum dynamics. By now, he had moved to the University of Oxford, and when I went to ask him for a job, he said, "You've come at the right time, because I've just landed this big grant. Would you like a postdoc for 5 years?" So I felt like I'd found the Holy Grail, because everybody else was sort of looking for 6 months or a year posts, and I had something secure for 5 years. And along the way, I got what was called a Ramsay Memorial Fellowship, which gave me the opportunity to do my own research as well, and combine the work I was doing with David with the sort of stuff I'd done previously with Steve. At the end of that, I went back to UCL Chemistry. These are some of the other people during the Oxford years. Mark Child literally wrote the book on molecular collisions. The best thing about Mark was, as an emeritus professor, what he did was he'd have tea every morning, and you'd go and sit in the tea room and you'd chat with him, and you'd chat about the work you were doing, and then all of a sudden you were talking about gardening, and you never quite knew where you were. And this, of course, was Tuesday evening in the old bookbinders in Jericho, which went pub quiz night, which was a pint, a burger, and really bad answers to very easy questions in the quiz. Back to UCL. Mike Ewing again, absolutely fantastic mentor as I entered my professional career as an academic. My first PhD student, Marion, who was just pure joy to supervise, simply because of her amazing enthusiasm for life and all that she did. And the fact that she didn't mind telling me to my face when I was getting it wrong, and just literally giving it to me straight. And then Björgvin. Now, I mentioned Andrea before. He linked me up with Björgvin, who was over in Uppsala, and I was invited over there to do some work, and that's a collaboration that persists to this day. It's just a really positive person to do research with. And along the way, out of the blue, Peter invited me. Now, this is Professor Peter Holdsworth, who I was introduced to by Steve in the first week of my PhD. And at that time, I didn't know what was going on. I was struggling to get my head around all of these things. And Peter was a scarily clever physicist who years later, out of the blue, wrote to me and said, "I had an idea. What if... da, 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 da." And he invited me this time, bear in mind, when I went to UCL Chemistry, I was there initially as a teaching fellow. And as a teaching fellow, he invited me as a professeur invité première classe, no less. So first class invited professor down to the École Normale Supérieure de Lyon to do some work with him on this interesting system that he was looking at. And that was brilliant because it gave me a really nice result in a paper that we worked on together. But more than that, the best thing I got out of this time, a couple of months down in Lyon, was I met my wife. And so I got a really nice paper. And a year after the time, and it really was a year after, it was love at first sight. And a year later we were married, and that very quickly led on to further additions to the output from my Lyon experience in my children, Rosie and Pierre, and I'm really pleased that they're able to be here with me tonight. So, back to UCL, I moved on from chemistry to engineering. These are just some of the people that really were huge influences. Nigel Titchener-Hooker was the dean whilst I was director of education for many years, and I could not have asked for a more supportive person throughout that time. John, Eva, Alistair, I'm really delighted is able to be here tonight, Liz and Anna, and I put them there mainly for my benefit and just to recognise their contribution, but I won't dwell on all the individual things. And then over to King's College London, which is where I am now, into the danger territory. Because if I start naming people here, I'm really in trouble if I start leaving people out. So I'm going to let Reggie represent all of King's. I've been made incredibly welcome since I arrived from the sort of pariah up the road, and I thoroughly enjoy being here. So thank you all for the welcome. So the second part of the talk is a little bit more about science. And what I'd like to do is recognise that my career started off very research-focused. And it moved on fairly quickly as I left that research fellowship into more and more education-related roles. Well, at that time, largely teaching. But as I think I recognised in myself, and it was probably recognised in me by others, one of the things that I like to do is I like to get involved in trying to organise things and try to facilitate things to work a little bit better than I thought that they were working at the time. But all the way, as I morphed into more of those leadership roles, like Deputy Head of Department for a while and Director of Education and now Vice Dean, I have these constant images of the science that I've done and in some ways continue to do that keep coming back, and they influence how I think. So anybody who works with me now is going to get a little bit of an insight into why I say what I say in these endless committee meetings and so on. And the first thing is, there are three fundamental concepts, and they link to three particular research projects that I've been involved with. Well, one is that understanding different length scales is important. So that's thanks to PowerPoint, microscopic, mesoscopic, and macroscopic. And the particular thing here goes right back to my PhD, in fact, my first paper. And this was on the critical behaviour of what's known as the two-dimensional XY model. And I'm not going to go into details of what this model is, but suffice to say, you've got a lattice of some kind, and on each lattice point, and it's a square lattice in 2 dimensions, on each lattice point you have like a little magnet. And those magnets, they're all interacting with each other, and they can move around, but they're all moving around just in that 2-dimensional plane. And some of the motion looks a bit like that, and it looks fairly cooperative, that kind of motion. And if you take that out to long length scales, you can imagine a wave sort of sweeping through the system. Some of it looks a bit more like that. If you really heat your system up, everything's fairly independent, and the local fluctuations start to dominate. But what happens at a critical point, and really the result here, if anyone's interested, is the fact that there's a whole range of these critical points in the 2D XY model, from 0 temperature up to some finite temperature at which it stops being critical. And the question that we were trying to answer was, are they all effectively the same critical point? Do they all head towards the same critical fixed point, or are they different effective classes? And it turns out they're different, and that's what that really represents. But the point I'm trying to make with the link to my later work in education is the fact that at a critical point, you can't ignore any of the length scales. Fluctuations at short wavelengths or long wavelengths, they're all important. And that has real implications if you think about it in terms of a university. So there we go, highly correlated critical systems, all length scales are important. The other thing you get is something called critical slowing down. And that means that the ability of a system at a critical point to relax back to equilibrium after you give it a prod, well, that relaxation time gets longer and longer and longer. And this has implications for universities. My hypothesis is that universities are actually systems that exist at critical points. All length scales are important. The Vice-Chancellor makes a decision. There's only one Vice-Chancellor, but his decision is large and impacts everybody and impacts the overall university. But each of us, as individual, dare I say, microscopic entities, that's how I feel sometimes, but we are all individual parts of this larger whole. But there are many such parts, and you can't ignore either end of that spectrum. We all contribute to how the university works. And I think there's a lot that we can learn by thinking about these critical systems in relation to these things. And ultimately, this points to relying on strong communication. And I've put this in here, and the critical slowing down thing, I think, is really felt in higher education. If we are a critical system, if you ever felt in a university that somehow if things are not slightly out of equilibrium, we struggle sometimes to get a handle on that and bring it back. And I think that the design of our structures could look to some of these models for answers to how we handle it. And I actually have a research project planned which may try and deal with some of that. But the big picture versus detail thing is something that comes up a lot at universities. Some people see themselves as, I think in big pictures and I don't need to worry about the detail. Other people are very much The detail matters. Every box has to be ticked and everything has to be perfect, otherwise it's not going to work. And I think the reality is we need both, but we also need people who can translate between the groups. And that's where the systems start to work. Oh, there we go. That's gone a bit small. Fundamental concept 2. Global optimization does not mean everybody's always happy. So let's think about this. This relates to a concept in my work that I've done a little bit of research on, which is frustration, and frustration in magnetic systems in particular. And I'll explain this diagram in a minute, but you can imagine how you can think of something like a university, where what's good for the university as a whole might not be always good for everybody or every part. So this is the study, and this was in fact the work that came out of the time I spent in Lyon. Again, don't need to dwell on the fine details of the science, but effectively this all started actually with work that was pioneered by Steve and his colleagues back when I was an undergraduate actually, on materials called spin ices. And unlike the system that I put up before with the square grid, this is a three-dimensional grid of corner-sharing tetrahedra, so-called pyrochlore lattice. And the little spins, the little magnetic moments, don't point along the lattice bonds anymore. They point into and out of the tetrahedra. And this is a frustrated system, geometrically frustrated. And as a result of that frustration, you get these emergent phenomena. And one of the things that emerges are these things called magnetic monopoles, or emergent magnetic monopoles. If you've ever thought about what happens if you cut a magnet in half, you don't get a north going off here and a south going off there. You get two magnets, each of which has a north and a south. So the question that has caused a lot of intrigue over the years is, can you ever get a north and a south that are independent? The magnetic monopoles offered, and spin ice materials offered a way to look towards that kind of behavior. So Peter's what-if question when he asked me to Lyon was, what if we had not just a few of these things, but lots of them, and they all came together and they condensed into something that we could call a monopole crystal. And the interesting thing with that, and that's really interesting, because I believe, is that Jonathan Tennyson who's just walked in? Because Jonathan Tennyson used to teach me, I'm sure you're here for Giovanna, but you probably don't remember Jonathan, you used to teach me many years ago on molecular physics, so it's a great pleasure that you're able to be here. So anyway, what Peter wanted to know was what happened if we condense these things, and what happens is, what you find is these monopoles have a field, a magnetic field, that effectively splits, we called it fragments, into two parts, one of which has these individual fundamental microscopic moments contributing to an ordered phase, and one contributing to a disordered phase. And the ordered phase here, this is neutron scattering, a simulation, and this was a sort of jaw-drop moment in Lyon. We've got these peaks, these black peaks here representing Bragg peaks, really strong order, and this other scattering with these pinch points, which is very characteristic of an emergent Coulomb phase. And this was really interesting because you get these two things happening at the same time in the same system, coming from the same moments, and they're contributing to both. That's the physics of it, but the reason for including it here is because of this concept that it all arises from frustration. And this is the thing in the back of my head when I'm dealing with lots of these issues in the kind of stuff I do in my vice-deaning type role now. And you can explain frustration more easily in relation to anti-ferromagnets than this case. This is a frustrated ferromagnet, so I'm going to do it this way. Imagine that instead of squares, you have triangles, and instead of things wanting, on neighbouring sites, wanting both to point up at the same time, you want them to point in opposite directions. So you put this one on pointing down, you put that one pointing up. What do you do with the third one? You can't satisfy all of those bonds all at the same time. The system is frustrated. And so the global, if you stretch this out into multiple triangles all over the place, what you find is that the ground state for this system, the global solution is not the sum of everything being individually satisfied. And I think that applies to universities. We exist as an aggregated whole. We're not separate units. And we don't optimize the whole by everybody always having exactly the thing that's perfect for them. And I think that if we understand that, and we are able to communicate, and there's trust between the different scales, the different levels, and the different units, then what we can recognise is the give and take that that takes in order to make the university as a whole as successful as it can be. Okay, fundamental concept 3, because I'm getting my 5-minute left warning. Sometimes things must get worse before they get better. So this was the science. This related to the quantum dynamics. Very briefly, what you've got here is a methane molecule with something over here trying to pull it off. And the kind of work I used to do there was say, what's the quantum state of all of those things, and how do those different quantum states, if you do a quantum dynamics simulation of that, how do those states affect the rates at which those reactions occur? But this all relies on having these things, these curves, which are called potential energy curves. So some energy depending on some variable down here. And a chemist probably sees it more like this. You've got energy, you've got something that can change, you've got two states that are represented by some change in energy, and you want to get from this state to that state. And if you can do that, you get some energy out, and that lowers the system, and that's favourable. But you might have to go through some other state on the way, and that involves going over a potential energy barrier. And I think a lot of the work that we do very often, we know where we are, and we know where we want to be. But to get there, we've got to put up with this bit in the middle first. And the question is always, is what we get out, is the improvement worth the effort? You know, is it worth pushing the ball all the way up the hill in order to have the fun of rolling it down afterwards? And that's an equation that I think we're all, in various ways, wrestling with all the time. And I think this view of potential energy surfaces also plays into other things. And this relates to the work that Rachel mentioned on interdisciplinarity. Thought a lot about this in recent years, and I've been trying to come up with a way to represent interdisciplinary behaviour and the benefits of it to a wide audience. And I think potential energy surfaces, multi-dimensions, offer that. So here's somebody, and they want to do science, and they see science mapped out before them, and there's lots of it, until I had fun doing this kind of thing. And maybe at school they see 3 sciences, and obviously this one over here would be biology, this one would be physics, and the really big important one over here would be chemistry. And as they build their knowledge, what they find is that actually chemistry isn't just one thing. It's a bit of organic, inorganic, and physical, and you have to learn a bit to go up those levels. But maybe you have to go up one and down one and up one and down one. And as you go through, maybe you specialise a bit, and you find that each of those have sub-disciplines. And we specialise, and we do masters, and we do a PhD, and we find ourselves wandering through this landscape in our careers until we find that we've got our PhD, and we're really expert in one little bit, and we're sitting at the pinnacle of that. But then we come across a problem, and that problem requires somebody who's on that pinnacle over there. And that's okay, because I can just about see them, and I did a bit of this when I was an undergrad, so I kind of know what it is. And maybe that person, they might be willing to wander across, and maybe we can build a link and have a bit of a bridge between the two. But what if the person I needed wasn't there? What if they weren't in chemistry, physics, or biology? What if they were in biochemistry, or in some other part of the science landscape that I can't see from where I am, that I don't know about? Well, what we could ideally do is not just train people to meander through this landscape, but actually give them some tools and some skills that let them build a jetpack. And that jetpack is the set of things that's going to let them effectively fly over the landscape and see the broad picture. It doesn't mean you do away with the need for that disciplinary excellence, but it means you have people who can see the whole thing and build the links between the different parts. And then, of course, you have to colour it in the background because your children say it needs more sparkle. So that's my sort of take on potential energy surfaces, both as barriers to overcome, but also potentially a way to model how we do things in interdisciplinary science. So that's a little bit of a summary of how I see that relating to universities. And in a nutshell, it's been fun. I'm still enjoying it. Research is great, and I'm really pleased I'm getting to do a bit more of that than I used to. I'm loving the teaching, and I'm loving the fact that through what I do, I'm able to bring that together into some of the things that I do in what I hope is contributing in some small way to keeping all the wonderful things that I have the privilege of seeing everybody else do happening. So thank you very much, and it's been a real honour.
hand you these to your brief questions.
Well, good evening, everybody. It's a real honour and a real pleasure to be able to propose a vote of thanks for Simon for his lecture. As you've already seen, I'm Steve Bramwell from University College London, and I've learnt several things tonight. I just jotted them down. One is that Kings are stealing all our best people. Number two, always listen to your father when you're when you're doing the washing up. So Google AI told me that I shouldn't talk for more than 3 minutes for a vote of thanks, and so I'll try and stick to that. And it said it's because the audience will get bored. I don't know how it knows that, but there we go. Yeah. So I thought I'd like to sort of thank Simon for a really sort of interesting and inspiring lecture. As he mentioned, Simon's worked with some fantastic people over the years. He worked with Peter Ellsworth in Lyon, with David Clare in Oxford, Jürgen Hjorvas, who's on the Nobel Committee in Uppsala, Zoltán Rácz, I think, also in Hungary, and so on. And everyone who's worked with Simon agrees he's a fantastic collaborator, very, very smart, but also very, very pleasant, nice to work with, enthusiastic. And Simon mentioned some of his research group. He mentioned Marion, who was the lead author on that wonderful paper, and I have a vision from a conference that I was at a poster session where the room was empty apart from around Marion's poster, where everyone was clustered, and she was excitedly telling everybody everything, and everyone, all the other people they'd left their posters, they were there as well, you know, so that's really great. So in terms of the scientific message, I think it's great to make these analogies with complex interacting systems. Universities are complex interacting systems. As a head of department at UCL, I'd say my job was 50% frustration and 50% plumbing, to a first approximation. I think some of those analogies are really well made, with critical slowing down, with the importance of length scales, and so on. And I think it's kind of very appealing to sort of make analogies between universities and scientific systems, as it gives us some hope for understanding how to make universities function better for students and researchers and everybody. Okay, so it just remains for me then I'd like to thank the King's leadership, Rachel, for sort of putting on this event. I'd like to thank the support team, Steph, for doing that. For the support, I'd thank you, the audience, for coming to listen. So, and like to wish Simon all the best for his future career at King's. I'm sure it'll be wonderful, as it was at UCL. Thanks a lot.
And you get not just one, but two lectures this evening. So I have the honour of introducing Giovanna now. So as I mentioned, the common theme is our university down the road, which both our lecturers this evening joined us from. But Giovanna started her academic career doing her PhD at the University of Turin, then spent some time at Caltech and at the Institute of Astrophysics in Paris, taking on an Enrico Fermi chair at La Sapienza, yes, my pronunciation you'll need to correct, and then joined UCL as a Royal Society URF in 2007, where she did some wonderful work at UCL, and rising in the ranks and leadership, and taking on the role as head of astrophysics there. So her research is very, very interesting. We'll hear some more of it in a moment, but some of the things that particularly struck me as fascinating as we look at interdisciplinary work at King's is her experience of being PI on the European Space Agency aerial mission, which is the only telescope set up for doing a comprehensive survey of exoplanets, and also the understanding and appreciation of not only interdisciplinary science, but working externally and innovating and impact as co-founder and co-director of Blue Skies Space Limited, which is looking at developing Newcastle satellites to promote high-quality data for science communities. Now, here, joining us at NMES, a little newer in post than Simon, but already making a fantastic start as Vice Dean Research. And she's very much leading on promoting and fostering interdisciplinary science and engineering, and also in the work that we're doing on looking at how AI interacts in science, both in the way that AI is used within our science disciplines, but also promoting the idea of how we as scientists can be developing AI tools and foundations of AI. She's clearly Giovanna's got a huge passion for encouraging bottom-up and curiosity-driven research and ensuring that we have a really positive research culture where academics, researchers, PhD students can all thrive. So delighted to invite you to give your lecture, Giovanna. Thank you.
Thank you so much for your very kind words, Rachel, and good evening to everybody. It's great to see in the room so many people that I know from the past and from the present. It's a great honor and a great pleasure. So actually, my journey starts in a small town close to the Alps, where I grew up in the 70s and the 80s. Back then, there wasn't internet, there wasn't a mobile phone, no social media. And so my imagination was nurtured by Japanese anime on TV that were quite popular in Italy. And I'm saying this because most of these cartoons were referring to very evil aliens that were supposed to come and destroy the Earth, and you had all these scientists and engineers that had to build a robot and a spacecraft in order to defend the Earth. And so somehow that, and perhaps some of the movies from Hollywood, really got a little bit into my brain. And perhaps also was the time and the age, because we were during the Cold War, and so we were hearing about nuclear threats basically every day. And so perhaps it's not really so surprising that when I was 10, I told my parents that I wanted to study physics. They didn't really believe me too much. In the meantime, looking at the planets that we knew back then, were 9, the planets around our sun. There were 9 because Pluto was not yet demoted as a planet. But basically, when the time came, I did stick to my plans, and I went to physics at university. I went to University of Turin because back then this was the closest city to where I lived, and it would have been seen as very extravagant to go to a different city to do university. I was the first generation going to university, and so there was a little bit of pressure from my family. Already they thought it was very extravagant to study physics. They would have probably seen me more as a lawyer or as a medical doctor. But I was glad that in the end I really studied what I wanted. And I had this great opportunity to meet Professor Luigi Sertorio at a certain point in my career, who became the supervisor of my master thesis and then part of my PhD thesis. Luigi was not only an exceptional physicist. He came from the School of Amaldi in Rome, and he had traveled the world, working in the US, in Brussels, at CERN. But also, I think, on top of really teaching me how to do research, because I felt that you had to learn how to do research. It's not just something that you do when you're out of your courses and your undergrad. But he and his wife, Elga Schiff, who was also a scientist, a biologist working in the informatics department, I thought they were incredibly glamorous because they were traveling around the world, speak many languages, and I felt so provincial. I was coming from this small town, really never lived abroad. And so for me, it was really an opportunity to learn from them also what the world was about. And they were extremely encouraging to tell me, you have to go, you have to prove yourself, you have to try things, and I really appreciated that. And so here I am in this picture. During the master, I went to do my first presentation to an international conference. And this conference was in Prague, in a moment in time where East Europe and West Europe were not communicating so much. So I think it was really quite a unique opportunity for me, not only to learn and to hear about non-equilibrium thermodynamics from senior scientists, but also really to see in that moment in time this communication with a part of the world for which we didn't have so much knowledge. During my PhD, I came across the work of this British biologist, Lovelock, and I thought it was absolutely radical and incredible. I was quite smitten by that work because Lovelock, for the first time, tried to define how to look for a planet that is inhabited by life, with a definition that is very scientific, and you can really try to find some evidence for it. And he had this first concept of biosignature, meaning, according to him, if a planet is hosted by life, then if you look at the chemistry of the atmosphere of that planet, it shouldn't be at the equilibrium, but you should expect that life is actually driving the chemistry out of equilibrium. And through this information, something that in principle you can also measure from afar, then you can understand whether the planet potentially is a candidate for hosting life or not. And I thought this was really, really incredible. Reading his book, it was basically telling the readers about his experience at Jet Propulsion Laboratory, how we became a consultant of NASA for the mission Mariner for Mars in order to look for biosignature. And again, perhaps it's not a surprise that after reading that, I thought that I really wanted to go to the US because I thought that this was really a topic that I really wanted to follow up. And so I discovered in those years that in the meantime in the US there was the NASA Astrobiology Institute, was a new institute of a number of institutes dispersed around the country. And I started to send my CV and cover letter to see whether they could have a postdoc for me to offer when I finished my PhD. And to my surprise, two places in particular, Carnegie Washington and Jet Propulsion Laboratory, answered. And they offered me to go and meet them and give a seminar. And clearly I was extremely excited. Went to the US in January 2001. In Washington, there was a snowstorm. And then I went to California, and on the contrary, everybody was out with their convertible. There was an Indian summer. So you probably guess where I accepted to do my postdoc. But actually, it really started at amazing part of my career. It didn't start it as well because I started my postdoc in October 2001, and it was immediately after September 11. And although when I flew there, they told me everything would be fine. When I arrived, nothing was fine at all. My visa was no longer really valid to go to a NASA center. I had to be parked University of Southern California for a while, and because of that, I couldn't be paid. And so here I was on the other side of the world, couldn't be paid with a visa that was not really entirely okay. And my mom and some of my friends were calling me, asking me, is everything all right? And I said, of course, everything is absolutely brilliant. I guess when you're in your training, you're also a little bit stubborn. But things then were adjusted. And in particular, in my years in the US, I ended up staying about 5 years. Had the opportunity to meet many people, both at JPL, but also in Caltech. And the figure here at the top is Professor Yak Young, who is he's still a professor in Caltech. And he had this amazing team of people. Not only absolutely exceptional in his knowledge of planets, planetary atmosphere, chemistry, and remote sensing, but also what I love of his team was the culture. Despite the fact that JPL and in general the user environment can be quite fierce in terms of, and quite aggressive when it comes to competition, I love the fact that the group of Yak was always really a bubble where you could go and just discuss science idea and always be supported. We had meetings on Sunday because they didn't want to lose time during the week. But apart from that, if you were okay in sacrificing your Sunday, then everything was absolutely fantastic. So perhaps coming to a little bit closer to the present. I show you that in the 90s, the only planets that we knew were the planets in our own solar system. But actually, since the 90s, planets around our star started to be discovered. A Nobel Prize to physics to Major and Claude for the discovery in 1995, or the first planets around Sun times star. And today, we really have planets everywhere. The discovery of planets is continuing. And statistically speaking, we're expecting to have as many planets as stars in our galaxy. So we are literally just in the Milky Way talking about billions of planets. We don't know yet all these billions of planets, but the counting has gone up to more than 6,000, being discovered with all sorts of technique. Many of them are organized in planetary system, and sometimes even with multiple stars. I think what is incredible of exoplanets is that it's true to say that truth is stranger than fiction when it comes to this. And although I'm using some images from science fiction movie that I'm sure you have seen, Interstellar or Star Wars, for each of these pictures, we have classes of planets at the moment that are unknown. And so in a certain sense, that's what I'm saying, it's well beyond the science fiction. We have planets that are orbiting so close to the star. In certain cases, they're completing their orbit in less than 1 day. You're talking about a temperature at the surface, if the planet is rocky, that basically is melting the surface. And so these are literally lava planets. We have, on the contrary, planets that are extremely far away and they're frozen. Some might resemble these ocean planets that you had in Interstellar. And again, we have many planets discovered that are orbiting two stars. So again, science fiction is not really science fiction when it comes to this area of research. To me, even more surprising, the most common planets discovered, in particularly closer to the star, this is where the sensitivity of some of the techniques at the moment is. Since you indicated most planets, the most common one, are actually in between the size of the Earth and the size of Neptune, so we're calling them super-Earths. But apart from that, we don't know exactly what these objects are, in part because they don't exist in our own solar system. From the density of some of these super-Earths, we understand they could be either rocky or rocky with some gas. In some other cases, they are less dense, suggesting more of the interior with ice and rocky and gas, or combination of many things. And there are even more exotic sort of scenario that we can think of. We believe that all this diversity must come from the processes, physical and chemical processes with which these planets are formed. Planets are forming in disks of gas, of ices and dust around the stars. The star at the center is evolving in the meantime, is a protostar. And basically all this material is gravitating and turning around the star, and clearly all this material sometimes is coalescing and accreting, and that's how planets are forming. This qualitatively, when it comes to real details, it's not that we know so well exactly what is happening. But the experiment at the moment is really highlighting the complexity of this environment where the planets are forming these disks. What you're seeing on the left is a collection of images coming from ALMA, which is a facility in the Atacama Desert that is an interferometer, very sensitive in the millimeter wave. And so you're basically probing the cold dust and ices of these disks. And all the structure that you're seeing are all very diverse sort of disks where these planets are forming. ALMA is probing also the chemistry of these disks, and also the chemistry is quite mind-blowing in terms of diversity. Many molecules are really complex molecules, a sort of prebiotic. And so the message that we are really getting is that, the molecules that are the precursor of life are actually quite common in star-forming region. So again, it tells us something. But also from the solar system perspective, more and more in situ measurements of meteorites or moons or asteroids, in particular getting to the level of measuring the isotopes, it started to tell us a little bit of a clock of how the solar system formed. So altogether, we start to get more and more constraints to the kind of picture that we have in one mind of how planets might form and evolve. But still, we still have many questions. How many flavors of planets do exist? Because although we have all these planets being discovered, not for all of them we know so much. And in particular, if on top of the density, you're also able to probe the chemical composition of the atmosphere, the temperature, the structure of these atmospheres, then we will know much more about these planets. Can we do this? We're talking about objects that are tens or 100 light years away from us, and most of these signals are really tiny. We're talking about 10 part per million or so. Can we do this? The answer is yes. And we started to do that not a long time ago. This is basically a plot that comes out of a paper that we co-published with Jonathan about water vapor being present in one of these big gaseous planets orbiting very close to the star with this unpronounceable name, HD 189733b. Now, that was the first because it was the first that we tried using the telescope Spitzer, looking in the infrared, to probe some molecule in one of these faraway planets. It was the first because before, most of the attempts were looking at different wavelengths, but molecules, in particular water, do absorb in infrared. So you don't want to look in the optical lower part of the spectrum. And to our surprise, although we could get only 3 points, so this were what was available with that telescope, these 3 points were suggesting that something was going on and absorbing in the atmosphere. And so that was the suggestion that we made in our paper, that possibly this kind of signal could be explained by the presence of water vapor, so trace gas in that atmosphere. Clearly, 3 points, you can fit many things, and we were aware of that. But that was the start. And at the same time, it was also the start of the collaboration between Jonathan and his team and myself. That's why I'm at UCL. I went to UCL to give a seminar, and back then I couldn't fit even the 3 points with the model I had. And Jonathan was in the audience, and he said, what line list are you using? And he said it, and he said, well, that's wrong. We use ours. And in fact, it worked. So clearly having the right line list is always good. But I think what was also good of this measurement is although it became controversial because, again, 3 points, you can fit a lot of things, and so it certainly sparked some debates in the community. I think it was really good that in order to answer to those questions and to these unknowns, we decided to step up. And in particular, back then, I got in USC, so I had the possibility to hire a team of students and postdocs. And the way to step up was to try new techniques of machine learning to see where we could statistically extract in a more objective way some of the information out of this data. And it went very well, not necessarily only for these 3 points, but for the many other points and spectra that we got later on. And there are a number of techniques that the team I had the pleasure to have at UCL was able to put forward. And most of the techniques seem to be extremely successful to get rid of instrument systematics, stellar activity, so successful that some of my colleagues, like Ingo Wollman, is using them very successfully for a company that is very successful to do this for defense. So clearly this technique do work, and not only for exoplanets. And we use also this technique for studies of populations of planets, not just single planets, because we start to have information of atmosphere for tens of exoplanets. And perhaps I have one extra example about some data that are more recent, taken with the James Webb Space Telescope, that is one of the biggest ever built, 6.5 meter telescope, very sensitive, so clearly an enormous step forward compared to the previous telescope. But still, if you're pushing for planets that are small and cold, like this K218b that is in the so-called habitable zone of the star, then even Webb is struggling a little bit. The signal are very small. But as you can see in this data that were interpreted by but Wen Liu, who is in the room, we are able to see some of the molecules and potentially also the presence of ACEs in a way that clearly in the past we couldn't, even for more challenging sort of spectra. More in general, throughout the years, I had the incredible opportunity of meeting extraordinary people at UCL, younger people, and I learned really a lot from them. And together we had a number of initiatives. In particular, we were quite committed to open science. And that's why we started to have as open source all our tools to make sure that everything is very transparent. I see Ahmed in the audience. He has been championing with all these great tools, really these initiatives. So I have 5 minutes left. And so in these 5 minutes, I just want to say something about instrumentation, because great to step up in better model, great to step up to have a better way of dealing with the data. But at the end, if you have a dedicated instrument that is really built to do one thing very well, well, that's even better. And with this idea in time, we proposed to the European Space Agency back in 2015 the mission Ariel. What we wanted to do was one thing and do it well. Being able to probe spectroscopically the atmosphere of exoplanets. And to do that, we wanted to have a wavelength range being covered in one shot between the visible wavelength down to the infrared, because we wanted to make sure to be very effective in doing this for about 1,000 exoplanet atmospheres. So really stepping up in terms of number and statistics. Now, behind the Ariel, that has been adopted and it will be launched in 2031, there is really an army of people, more than 600 scientists and engineers coming from 16 ESA countries, NASA, JAXA, and the Canadian Space Agency. And that's the reason why we are saying Ariel mission is a space telescope, but is a mission because there is more than flying hardware. When you start to have an army of people working on something for years and years, I think that sounds like we're all working together with a similar goal, and that's where the word mission really becomes meaningful. At the moment, the mission is being, the payload is being tested and assembled at Royal Space here not very far away in Didcot. Hopefully everything will be okay. And when all these testing campaign and integration is finished, it will be sent to Airbus or the prime for the spacecraft to be launched. I mentioned before the importance of using machine learning technique to get rid of some systematics or improve the data. And that's where AI today is really as good and as important as the hardware. And it's very clear to us in the Ariel consortium that we need to make sure that AI is integrated since the beginning with Ariel. And Gordon Ip here in the room is championing really this work through the data challenges. It's the 6th year now that we're running the data challenges, and in particular in the last 2 years they were hosted by NeurIPS. And there was a prize from Kaggle of $50,000, which is clearly an incentive for people to participate. And they've been quite amazing, not only in the output or how helpful has been their solution to improve the performance of Ariel, but also in terms of making sure that we are aware of the great techniques that are being considered around the world and how we can channel them to do something that is related to this mission. The openness of Ariel is not just related to the data, but also in all the databases, in all the tools that we are making as a consortium, all available to the community, all transparent, all available through this link tree that Bex Coates, also here at King's, has put together. And perhaps a brief mention to the exoclock exercise that was started basically as an initiative by back then two PhD students, Andros Tiaras and Anastasia Kokori. but now has become quite an extremely successful initiative and program. ExoClock was born to solve a problem for Ariel, identifying exactly the position of the planets that we will look into. And to do that, they were able to summon all the community amateur astronomers around the world, that now is including more than 2,000 participants from 70 countries. More than most of them are amateurs. They're really spread all over. And all these great high-impact papers that they've been writing, co-authoring with all these very long list of amateurs, has become something that everybody's very proud of because of the great outcome and because of the participation, the global participation. I'm conscious of time, and so I have a couple of slides before I get to the end, but Rachel mentioned Blue Sky Space, and that's something also I'm very proud of, also in particular because our two co-founder, Jonathan Tomlinson and Marcel Tassanir, are here in the room. We started back in 2014, and it looked like a little bit of a crazy idea from three academics. And in part was because we wanted to see whether we could launch satellites outside, basically, the remit of some of the government space agency. There's nothing bad with space agency doing space missions, but most of the time you really need to do that if you're going for something extremely ambitious and expensive. But in a new space economy, there are all sorts of satellites nowadays that can come off the shelf with a price tag that, I don't want to say they're cheap, but they become comfortably similar in terms of cost to our ground-based equipment. And so that's how we had this idea of creating Blue Sky Space to make sure that we could launch more small satellites for science and basically sell the data as a commodity to all the scientific community. So clearly trying to serve all the science communities that wanted to have a specific type of data. Our first satellite MOV was supposed to launch this week, actually, on Monday, but because of the FAA situation is probably delayed to next week, so we're all quite excited about this opportunity. We go up with a Sport at 15. Company is no longer perhaps a startup. We start to be a scale-up. And also we have a lot of ambition because MOV is our first satellite, but we already have a number of other satellites in preparation and design phase. And we find it is particularly exciting, and hopefully everything will be fine with the launch of MOV. And so this brings me to my last slide. I think the opportunity to come to King's really arrived at the right time in my career. I was perhaps looking for a new challenge, a new chapter, and I think was an extraordinary opportunity what I had from King's, because as Richard said, as you probably have seen throughout the slides and my career in life, my interest is not perhaps with one science only. I had interests that are really touch many types of science. And in this new role of Vice Dean, I'm really extremely happy and honored to be able to work with incredible scientists across the department of NMES and also outside NMES. So I'm very grateful of this opportunity. I'm really looking forward to work with you all. And my very, very last slide is just to say that out of what we learned to extrasolar planets, we don't have an Earth 2.0. So we don't have a plan B. And even if there were a Earth 2.0, they're really, really far away. And so I think we really need to take care of this one, something that extrasolar planets are reminding us every minute, every day, every time, because we don't know if we have another planet to go to. And so we really need to take care of the Earth. Thank you so much for your time.
Thank you. So I'm just going to say a few words in thanks to Giovanna and then close with some overall observations. The first thing to say is, being of a similar generation, I remember being gutted when finding out that Pluto was no longer a planet. It was extremely disappointing, But I feel I've kind of got a little bit more hope now, knowing that there's as many planets as stars. So, you know, I'm gonna park that sadness and look more hopeful now. More seriously, though, I think it's been a wonderful talk, really highlighting the interdisciplinary, the essential interdisciplinary nature of your research. How you've brought together thinking from biology, from physics, from chemistry, and new techniques from AI, machine learning, and other tools out there, to follow your passion, to discover and understand what's happening out there in the world, finding out incredible things about the diversity of exoplanets, and doing so in a way that where collaboration is absolutely key and essential in delivering this. I like the statement too about that discovery of exoplanets, that truth is stranger than fiction. And as we think about interdisciplinary work, I think we absolutely shouldn't lose touch of the fact that what can sometimes drive our creative thinking is work outside the science interdisciplinary, but that work of creativity, be it the Star Wars, be it the films, be it art, and I think that's something that's really important in NMES. We have the quantum entangled at Science Gallery, and that creative thinking beyond just the sciences is really important. So in collaboration, I find it an incredible piece when we hear about the annual mission, which really is a mission. Scientists, engineers from across Europe, US, Canada, Japan, working together in this collaborative way to achieve a shared mission. As well as achieving this shared mission, I think it's a real example of how soft diplomacy, how scientists, how we kind of can contribute, and it gives some hope when you see so much other things that are happening in the news, to see that we can collaborate, we can lead on this type of work. So thank you for sharing your passion, your excitement, and all your achievements with us, and we are very much so glad that you're with us, and we'll still talk to people down the road and still collaborate with them, but we're very glad you're here. So just to kind of close, generally I think we've had two extraordinary talks this evening, and it's been an absolute pleasure hearing those. I think it's very, very clear from both talks the importance of what we do in our sector in higher education, how we open doors and inspire students, and particularly professors. You have a responsibility in the leadership of the university to inspire, support, encourage our students, undergraduate PhD students, also our earlier career academics, to support and inspire. And then I kind of think final analogy for me is, as Vice Deans working as a faculty leadership, I think, we spend quite a lot of time having to push up that activation energy to solve problems and to bring people along. So it's quite a lot of pushing up the hump. But hopefully the ambition is to get to a better place, to be able to make positive improvements so that students and staff can thrive and excel in our great faculty and wonderful university. So thank you both so much for tonight. There are some drinks, I think, in the Somerset room, so please do join us and to continue celebrating with our inaugural lecturers this evening. Thank you.